Welcome back to the RSET training, Landslide Monitoring and Risk Assessment using NASA Earth System Data. My name is Sean McCartney. I'm an RSET trainer at NASA's Goddard Space Flight Center. I'm pleased to welcome you all to the third and final part of the webinar series. The following slides provide an overview of the training. Over these 2 weeks, we've learned about remote sensing for landslide science and disaster planning in Part 1, planning landslide occurrence using Earth observations in Part 2, and today we'll be learning about remote sensing and landslide susceptibility. All materials and recordings from each session can be accessed from the training webpage. If you were not able to attend one part, all recordings are available on the RSET training webpage. Homework opens today, March 18th, and will be due on April 1st. You can access the homework from the training page. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment by the given due date. The prerequisite for the training is our Fundamentals of Remote Sensing course. We recently relaunched a new online, self-paced Fundamentals of Remote Sensing training on the RSET Learning Management System, and we hope you will check it out and share this training with others. Please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go. The Q&A document will be posted to the training website within a week of today's training. By the end of this 3-part training, participants will be able to identify the core concepts of landslide risk mapping, including geophysical and meteorological drivers, and how satellite data can be used for this purpose. Select appropriate satellite data and model data to support landslide science and disaster preparedness associated with landslides, and recognize how to map where landslides have occurred using optical and radar data, and understand how automated tools can be used for this purpose. Part 3 of the training is focused on remote sensing and landslide susceptibility. I am delighted to reintroduce once again the guest trainer for today's webinar, Dr. Robert Emberson. Robert serves as Associate Program Manager for NASA's Earth Applied Sciences Disaster Program Area. In this role, he helps administrate a range of projects funded by the Disasters Program, as well as supporting the disaster response activities by providing satellite data and insight to a range of stakeholders before, during, and after disasters strike. Alongside this programmatic role, Robert is also part of the NASA Landslides research team, where his current research focuses on how to better understand and model the exposure and risk faced by human settlement due to landsliding. The primary aim of his work is to better model the economic and social impacts of landslides globally and in near real time using satellite data. Robert, over to you.
Okay, well, thank you so much for the introduction again, Sean. I'm delighted to be here again for the third part of this training on landslides and satellite data. Today we're going to be talking about landslide susceptibility and hazards. There's a bunch of different topics in here that I'm excited to cover with you all. We're going to start off talking about landslide susceptibility and what that means and how it can be conceptualized. So yeah, we'll kick off. So the first thing to do is to talk a little bit about what defines landslide susceptibility. In a large-scale review, Reichenbach and co-authors defined landslide susceptibility as the likelihood of a landslide occurring in an area on the basis of local terrain and environmental conditions. So this is obviously a likelihood. It's thinking about the potential chance of a landslide happening. And so I want to talk about this in the context of some other terms you may have heard relating to impact and disasters. So susceptibility, we think about this as where is the landslide likely to occur. Hazard is both encapsulates the where of the landslide, but also the when the landslide is likely to happen. So thinking about the timing of that event. The next question we could ask and think about is exposure, and we talked a bit about this in the first 2 parts of this training, but we're thinking about who or what might be in the zone that is hazardous. And then vulnerability is a more kind of nuanced term that is thinking about how likely is damage or injury to occur as a result of this level of exposure. And finally, a term that is widely used is risk. And based on global definitions, risk is hazard multiplied by exposure multiplied by vulnerability. So essentially the impact of a hazard consists of both the exposed population and their potential vulnerability. So it's important to note, as we've talked about before, that exposure and vulnerability are typically more challenging to assess from satellite data, and vulnerability in particular, considering that it consists of various socioeconomic and maybe like less quantifiable pieces of information. But today we're going to focus on susceptibility and hazard. So thinking about susceptibility, there are obviously triggers that obviously set off a landslide. We talked about these in the first part of the training: high intensity precipitation, as well as the potential glacial melt or earthquakes. This figure here is showing both the kind of potential impacts as well, so the loss of capital or damage to infrastructure. But what factors affect susceptibility, and how can we observe them? So that's the question we're going to ask in the next few slides. Before we do that, one further definitional element to consider is thinking about the way that landslides exist in the landscape. So, as we've spoken about before, landslides typically, or essentially always, originate at the top of a hill or near a higher up a hill slope, and the impacts in that landslide can be felt further downslope as the gravitational movement occurs. So, susceptibility is described in the areas where a landslide is likely to originate, or the source area. But as you can see in this figure, obviously the runout of that material has impacted downstream places and downhill locations, including this road. So hazard is thinking more about the potential for impact or potential for hazard to occur all the way across this landslide scar, even if it's not where the original source area occurs. And so there is certainly a difference between these locations, either like higher up in the slope versus lower down on the slope. And so these potential differences in source versus runout areas must be something we consider when we're building susceptibility models. So I'd encourage you to think about that as we talk through some of these other elements. But let's talk through some factors that can affect susceptibility and how we can use satellite data to assess those. So the most, I think, important factor that most of you would recognize is slope. The difference between steep slopes and shallow slopes certainly strongly affects the likelihood of landsliding, as you can imagine. As you increase the slope, the potential for the frictional angle or the potential frictional resistance to sliding decreases proportional to the weight. And so slope is one of the things that we would consider most strongly. And we can assess this with digital elevation models. This is a pretty standard technique to build slope assessment using either open source or proprietary GIS software. And this often forms the fundamental basis of most susceptibility analyses. More complicated analyses might include things like average upstream slope. And so we would think about potentially the location of an individual point in a landscape and thinking about the areas upstream of that, so the places that drain into that slope, into that that location, and the average angle associated with that. So in this case, I've shown an example from Kenya, and this is a very graphic figure, is showing the color scheme has higher and more intense red colors for a higher average slope up in those individual places. And what this might mean is thinking about locations where potential hazard is higher. So instead of the location that things might start, average upstream angle might indicate locations where there is a higher upstream slope. And as a result, those places might be more likely to have runout. So this is the kind of thing you can start thinking about when it comes to either susceptibility or hazard, and thinking about the differences between more sort of static factors like slope or more kind of a derived analyses like average upstream slope. Another factor that is widely assessed from digital elevation models is compound topographic index. This is also widely referred to as wetness index. What this essentially refers to as it combines both the slope and the flow accumulation in a landscape. And this is another way of thinking about locations where water might be most likely to be flowing through a landscape. This kind of schematic example here is showing the higher values in blue and the lower values in red. These are locations typically flagging channels or river channels, typically at the base of hill slopes. But because we know that water saturation is an important control on the location of landslides, the topographic index or wetness index may be another strong control, or at least proxy, for the locations where landslides might occur. So again, this is another data set that we could incorporate into a susceptibility analysis. People talk a lot about roughness of a landscape or ruggedness of a landscape. There are several terminologies used. Topographic ruggedness index, for example, TRI, describes the difference between elevation between a point and the neighboring points around it. And you can imagine this because obviously places in the landscape that might have a more rough terrain might be less smooth as a result of soil cover. These might be places where there's more convexities or concavities that might be likely to have changes in friction, and as a result, potential landslide likelihood increases in potential landslide likelihood. So this is again a more derived assessment. I'm showing an example of an image from Taiwan here, where you can see obviously there's lots of like rocky outcrops and landscapes where landslides are often occurring. You might see a lot more of these kind of like rocky outcrops, and so topographic roughness is another factor that may be important. Furthermore, you could think about the position of a point in a landscape. People have developed systems called topographic position. Topographic position index, particularly, is a kind of used in some analyses. And this describes the relative location of a point within a larger landscape. And so you can think about this as places that have a high topographic position index would be typically on a it would describe that this is a higher point in the landscape relative to its neighbors. That might describe something like a ridge, or and a lower topographic position index might describe a valley. But if you assess that over larger length scales, so larger neighborhoods, we can think about topographic position index as a kind of at this larger scale, and thinking about like the broader parts of a landscape where landslides might be likely. And so again, high steep slopes and like points at the top of steep slopes might be places where earthquake triggered landslides may be most likely to occur. We spoke about that before. And so again, using this kind of more derived classification of landscape position might be an additional source of information when describing landslides. So again, all of these systems are relevant to think about when we're thinking about the location of a landslide, particularly within the topography. And all of this can be characterized using digital elevation models. There are other characteristics, things like curvature or aspect of a slope. Aspect in particular may be relevant for landslides in locations where freeze-thaw weathering may be involved, because those are the kind of slopes either facing north or facing south, where there's a predominantly increased amount of like freeze-thaw cycles in some parts of the world. Those may also be places where landscapes are likely to have increased landslides because of reduced strength of the rock. So again, there's lots of different elements we can incorporate, but ultimately at the core of all of these is digital elevation models. And these can be sourced from a lot of different places. From NASA, the NASA DEM data is highly relevant and widely used in this process. And you can access that through the Land Processes Distributed Active Archive Center, or DAC. In some locations, there may be data sets that might be high resolution, particularly thinking about within the US, there may be sources of information relating to high resolution LiDAR, for example, and you can find that through other sources. Yes. And an additional source of information is open topography. This is an excellent open source resource for other DEM data around the world. So how would we assess the locations within a landscape using a DEM? So a DEM is obviously a raster data set, and it consists of pixels. And so what we would think about is trying to compare the pixels where landslides occur and looking at the distribution of those values of some parameter, in this case potentially slope or roughness, for example, and comparing that with the frequency or probability of that sort of parameter in non-landslide areas. And so we can build a kind of comparative model of those two different kind of populations of pixels, and then building something like a likelihood ratio. This is a way to like assess the relative likelihood of a landslide pixel relative to the rest of the landscape. For a given parameter, we can build this kind of estimate of a ratio for these two different sources of information. One of the reasons we do this is because we can compare the pixels associated with a landslide has occurred, so the source area, but also where it's triggered, the source area, but also the locations, the pixels associated with a landslide runout. And that allows us to compare sort of two different distributions of landslide pixels, let's say, both the source and the runout areas. And so why does this matter? Well, so here's an example from a whole series of landslide inventories taken from a number of locations around the world. And here we're looking at compound topographic index, or wetness index. And the x-axis of this figure is showing the relative compound topographic index versus relative to the landscape. And so you can imagine higher values here are where there are higher wetness index values. In other words, like where landslides are most likely to be higher potential water accumulation locations, and the left-hand side is places where there's like lower water accumulation. And the probability ratio is telling us something about where landslides are, the likelihood of a landslide pixel in that for that given value. What you can see in the left-hand box here is that there is lower compound topographic index values, so lower potential wetness in the landscape. The likelihood of a landslide scar is higher than it would be at those higher compound topographic index values. So in other words, landslides scars are more likely to be found in potentially drier parts of the landscape. And so that's kind of an interesting analysis, but obviously it makes sense in some ways because the potential location where landslide occurs is less likely to occur in the deep valley bottoms than it is potentially halfway up or at the top of a slope. So maybe in this case, we're seeing that wetness is not the only control here. Slope may be more important. But the right-hand box here really makes this point more important, because when we look at the entire landslide area, not just the source area, the scar area, you can see that we no longer see such a strong connection between those low CTI values and the source and the likelihood of a landslide. In other words, the runout zone of a landslide, the deposit area, is also found in locations which are topographic, potentially wetter areas or potentially topographic hollows. And so in essence, what we're seeing is that there is a difference between the source and the runout areas, and we can see this when we're analyzing the DEMs. And this really is important when we think about susceptibility, because we want to know the likelihood of a landslide occurring in a given location. That is associated with where the landslide scar occurs, rather than where the landslide runs out to. Obviously, we can think about more of that, like occurrence, potential runout models. We can talk about that. But in general, the scar assessment allows us to assess the potential for a landslide to trigger in a given location. And that's why it really matters to distinguish between those two areas within a landslide. So there are some other factors, of course, associated with where landslides occur. Land use is critical. We talked a lot about how the type of either forest cover or agricultural land use or otherwise may be a strong control on the slope stability. There are a wide variety of different Earth observation data sets that can be used to assess land use. MODIS has been widely used for many, many years, but Sentinel and Landsat have more recently become widely available and used to build high resolution or moderate resolution land use data sets. These are often available in both open source platforms and through archive centers, and I encourage you to explore different land use characterizations. Obviously, this is a different kind of data. It's not a continuous data set. It is a categorical data set. We'll talk more about that shortly. But in general, this is another important factor that could be considered during landslide susceptibility analysis. Soil thickness is a further factor that could be considered and has widely been used. Here is an image of the estimate of soil thickness for much of the kind of Bangladesh and Southeast Asian region. Typically, increasing soil thickness may be strongly associated with smoother, more kind of longer-lived hill slopes, whereas thinner soils might be in more steep landscapes. And so the likelihood of a landslide occurring in a given location might be correlated with soil thickness. This data set on soil thickness can be found at the Oak Ridge National Laboratory DAC, again, sourced as kind of through the NASA's DAC architecture. And so there are relevant data sets here that could be exploited for further analysis. As mentioned, land cover is important, but particularly changes in land cover may also influence the sort of stability of a given landscape. If deforestation occurs, the location of a landslide might be more likely to occur in a recently deforested area because the vegetation that has potentially previously been binding a hill slope together is now lost. And so we can assess things like forest loss using a number of different land cover data sets and derived data sets from that. There is a moderate resolution Landsat derived annual forest loss assessment that was produced using NASA data. And this has been used by NASA teams supported by the Disasters Program, for example, to assess the likelihood of landslides occurring in a given specific location as a result of forest loss. Underlying a lot of landslide locations is lithology, things like faults, the location of different rock types, and the kind of structure of the rock itself. Those factors are very important. Typically, this is a much harder thing to assess from satellite observations, and so there are many data sets and studies that use more local analysis and field studies. But it's worth noting that there is a new generation of satellite data sets that have been produced using hyperspectral data that potentially have begun to think about how we can assess the lithology or the bedrock assessment using hyperspectral data. So that's an exciting topic for the future. But at the moment, typically landslide susceptibility studies would use field analysis of lithology as their source if they're using a lithological input. So in summary, there are a wide variety of different factors that go into landslide susceptibility. A large study of several thousand landslide susceptibility assessments produced this I think estimate of what is the most commonly used factors within landslide susceptibility analysis, and you can see that morphological factors, including curvature, aspect, slope, are pretty critical in most of these things. There are other factors, however, like land cover, as I mentioned, very important. But then some other kind of less commonly used factors, like the potential long-term precipitation that might involve the just to kind of control some of those relevant land uses, or the distance to rivers as well as another factor here. And we often think about distance to river as a more kind of specific information rather than the derived estimate or proxy estimate from compound topographic index, as I mentioned before. So in summary, many different data sets are used, and there is no consistent kind of analysis. It depends a lot on the type of available data for a given location. Certainly satellite data can provide a wide variety of these sources of information, but in the case where there is more specific local information, that may be preferred for some examples. And so again, we can build a sort of a first order working model with a lot of satellite data, but ultimately field studies may be also critical to determine susceptibility going forward. And so again, I think summarizing this, we can say that landslide susceptibility analysis using satellite data can be relevant at local, but is very effective at regional and even global scale because we have the data set and it is generalized across the entire planet. We can build this assessment of the landslide locations and the potential differences between susceptible locations and non-susceptible locations using large landslide inventories and assess the differences between those pixels and non-landslide pixels. But one important factor to consider, and really the core of all of this, is that Earth observation data is really only a proxy for the physical reasons why landslides occur. In other words, we can't observe the frictional state of a hill slope from space. We are looking for factors that correlate with that rather than the causal factors there. And so typically we're not characterizing the kind of gravitational forces. And so ultimately most satellite-based models are statistical in nature. They produce correlation assessment of the differences between landslides and non-landslide locations. So more locally, there may be an availability of geoengineering tools or physics-based modeling using kind of an advanced field assessment of individual locations. And so it's important to note that that kind of analysis for susceptibility certainly continues and is widely used, but statistical approaches are much more typical for satellite-based data sets. So in the next part, I'm going to talk a bit about how we construct susceptibility models and what that means in essence. So as I mentioned, we're talking a lot about satellite data, and so we're thinking about statistical inputs and outputs and statistical models. What this means is that they use combinations of data associated with susceptibility, things that we just talked about, in combination with training data. And that training data, in essence, is where landslides have been observed to occur in the past. And the underlying assumption is that the locations where landslides have occurred in the past are likely to predict the locations where landslides will occur in the future. So there's an essential assumption that those locations are similar, and that typically holds good in many locations, but it's also worth pointing out that that is an underlying assumption behind all of this. In general, we then looking at those locations where landslides have occurred, we build relationships and assess those relationships and then generalize them, applying them to our kind of broader input data to create an output susceptibility map, which is essentially a prediction of the locations where landslides are likely. So, for example, in this very simple assessment, we could say at higher slope values, there is this relatively increased likelihood of landslides to occur. And a sort of single parameter model would be conceptually simple, but ultimately we have access to a lot of different data sets. And so we would think a lot about these more complicated multi-parameter models and how they would be kind of combined together. And so that's probably really important. So as I mentioned before, susceptibility model inputs and outputs typically would consist of these different input data sets associated with susceptibility, DEMs, land use, soil thickness, forest loss. But ultimately, carrying all this together is an inventory of landslide locations, a sort of data set of the places where landslides have been observed to occur. In this case, we're showing an image of a polygon data set of landslide mapped landslide locations. We would use that to then train a model that can then produce an output of susceptibility analysis. So this concept of a landslide inventory as training data set is important to drill into because landslide inventories can vary widely. And particularly if we're thinking about satellite data, we might have access to information available globally or locally. The disasters program at NASA has supported the Global Landslide Catalog through a series of research grants. The Global Landslide Catalog produced by the Landslides research team is a global assessment of where landslides have occurred in the past. And this has been produced using media reports as well as a number of kind of inputs from different data sources, but it is by no means comprehensive. And what I mean by that is it does not list the location of every landslide that's ever happened around the world. You can see here there's points, and there are obviously large sections of the world where we may have more limited access to media reports, or we may have confidence in those data sets, but it does not mean that there are no landslides occurring there. And for example, you can see that in some countries, English-speaking countries, the United States and the United Kingdom, for example, we see many landslides mapped in this data set, whereas in Sub-Saharan Africa, for example, we're seeing a lot fewer. And so there's certainly a completeness issue here. And at this stage, there is no long-term archive of every single landslide around the world. It might be we could point out that that has been something a lot of researchers have talked about as being possible now that we have access to long archives of satellite imagery. But at this stage, we still don't have access to that. So thinking a little bit about these large-scale global data sets, we can say at present that those are incomplete. And any kind of data set analysis will have to consider the level of completeness. Locally, we may have access to more complete data sets. I showed you that graph earlier, those set of graphs looking at the differences between landslide source area and landslide runout area. That was sourced from a series of analyses of landslide inventories for specific triggering storm events. Those are sourced from a number of locations around the world, and this map here is showing those locations. So we have access to some of more high resolution data that is in these kind of individual locations. And for example, this is from Zimbabwe in 2019. We had access to high resolution commercial data sets to map this. And again, through work supported by the disasters program, we were able to kind of produce landslide inventories for this kind of catchment area. And this is what we would then refer to as a complete landslide inventory for a location. We were able to look at every single location within that landscape and assess whether a landslide had occurred or not. And in essence, we were able to capture all of the landslides occurring in that given area. And so we would be able to use that as input for a landslide susceptibility modeling assessment. And we could essentially assume that the inputs there would be comprehensive in comparison to, for example, a more sporadic report-based inventory. So just important to stress that the concept of a landslide inventory can differ from these very localized, more complete inventories to kind of a global assessment that may be less comprehensive. Both can be helpful, but yeah, important to note that the two things differ. So to gather the information from the landslide locations, there are typically, this is based upon getting the pixels for those landslide locations. And if you have a fine resolution DEM data, for example, you might be able to get a lot of different pixels from an individual landslide. One could also take a point, as I guess a single point for each landslide and assess the variables at each of those points. In essence, though, we're looking for the likelihood at the point where a landslide occurs, or the pixels where a landslide occur, and getting the parameters associated with those pixels and the non-landslide pixels to build a kind of comprehensive data set. In more recent studies, a different approach has been taken, and that uses what's referred to as a slope unit. The important difference here is that obviously in a raster-based approach or pixel-based approach, if you have a very coarse DEM relative to the size of the landslides, you may be unable to the hill slips where the landslides may be occurring may not be effectively captured by the DEM itself. So in essence, you could have pixels that are overlapping the edge of a watershed and wouldn't be capturing the data there at all. And so slope unit-based approaches characterize areas as specific slope units. Essentially, this is an individual hill slope is mapped specifically as a polygon, and the analysis would then assess the parameters associated with that slope unit and the landslide area coverage within that slope unit. This has been widely used now in more recent studies, as it can, for example, avoid pixels cutting between two valleys. And so this is maybe something to explore in future, although, again, this is more novel in terms of the uptake in the community. In terms of the statistical methods used to combine the inputs and compare them with the landslide inventories, there is an enormous variety. Here I'm again drawing from this excellent review study by Reichenbach and co-authors in 2018, who showed that for thousands of different landslide susceptibility analyses, there was almost as many different types of statistical approaches, ranging from back in, I guess, several decades ago, more classical statistical methods, thinking about regression, to more modern approaches, which might include AI-based assessment or kind of neural network assessment, particularly machine learning. These elements are certainly more used in recent work, although there still remains a significant amount of classical statistical approaches as well. So NASA teams have used a number of these tools as well. We've used, I guess, the regression analysis, machine learning, and also more recently kind of neural network and AI-based approaches to assess susceptibility. It's obviously important to note that each of these different methods has a wide variety of concepts and understanding that needs to go into this. It is by no means, certainly within the context of this presentation, we don't have enough time to even dig into some of the most simplified versions of this, because many of the machine learning methods, for example, would be highly complicated. But in the critical rule of thumb for all of this, and what's underlying, I think, a lot of the science that has been done effectively, is that your outputs that you get out of a statistical model are only as good as the inputs that you're able to apply and put into that. And so in essence, if you have very poor input data, very coarse or very incomplete landslide inventories, or data sets on DEMs that may be kind of incomplete, or maybe you're only including one single parameter that could be considered, your outputs may not be very good. And so again, this just goes towards the factor that having a good field understanding of what causes landslides and what might lead to landslides, areas being more susceptible to landslides, underpins the use of different susceptibility models. And I think it's important to stress that once the sort of different input data sets are relevant, the analysis and the statistical method used, may be robust, just regardless of the kind of type of data set, type of method you use. In essence, good inputs and means good outputs in most cases. When thinking about these statistical models, I mentioned before that we have continuous and categorical data sets, and those are different things. So we, for example, talked about slope. That is a continuous data set, and that means it can take any value in a given range. So 0 to 90 degrees, for example. And there are many data sets that we would use that will be continuous. They're typically widely used in Earth observation, things like soil moisture, rainfall intensity, those factors that we would, again, think a lot about. However, there's a second type of data, categorical data, where the values are classified. So things like land use or lithology, where we're talking, there's not a 0 to 10 data set defining land use. It's is this forested? Is this agricultural? Is this impervious? Those are kind of conceptual categories rather than specific values. Each of those different categories can be a proxy or a correlation factor with the location where landslides are likely. So they still might be important data sets, but different statistical methods may treat those approaches differently, treat those different data sets differently. A good example is random forest modeling, which when applied can incorporate both continuous and categorical data, but for categorical data to achieve an effective accuracy and robustness with that, you would have essentially, there will be a lot more weight applied to categorical data unless it is converted into more continuous data sets. And so there are ways to approach this, and I would encourage you to review some of the resources associated with this presentation for more details. But in essence, the way in which those different data types are considered does matter for different statistical methods. And I, again, stress that understanding this is crucial before building any kind of statistical analysis. So let's look a bit at some of the outputs that we would generate. So here is NASA's global landslide susceptibility map. This was from a study in 2017. And has since been, I guess, updated. But here's a very good example of some of the earlier work that the team did here at NASA. And so you can see again, landslide susceptibility is flagged on a kind of slight to severe likelihood scale. As you can understand, the higher slope mountain ranges, typically the places where we see that increase in susceptibility, although there are certainly places all over the world where landslides may be more likely. This approach used what is referred to as a heuristic weighting of input factors. That's a more simplified approach where the input values were assigned a relative weight in the output assessment. And that was based on expert analysis. And typically this can be widely appropriate when, for example, this was trained using the Global Landslide Catalog, and that excellent but somewhat incomplete data set that is used globally. And so again, this was an effective use of kind of more, I guess, old school statistical methods, but more recently those have been updated to some things that we'll talk about in the next few slides. So a more local or regional example is another tool that we developed, again, supported by the Disasters Program, to assess the likelihood of landslide susceptibility in a sort of small part, to build a kind of small localized assessment for this. This model uses random forest approach, which essentially uses a number of decision trees. Essentially, you take a random subsample of the data set, you apply a decision tree assessment to that, and then that is done a number of times. The majority voting approach is taken, which leads to a final prediction. And so this allows us to produce a continuous probability estimate for a given location, for a given pixel, for the likelihood of a landslide, rather than, let's say, a categorical 1 or 0 landslide likelihood or not. This is effective to use a variety of different Earth observation data sets, and was built with simplified data processing in mind. And so an output example here is from looking at the Rohingya refugee camps in Bangladesh. This is some work that our team supported several years ago. And the higher red values here indicating higher potential susceptibility for those locations based on a number of different elements, including not only DEM data, but also land use, soil thickness, and forest loss. From those assessments, we can also get the relative importance of the individual factors. In this case, the slope and soil thickness were very important to the relative likelihood of landslides in that setting. Here you can see that the relative importance of the different land use characteristics are also included. So cropland and forest loss and the grasslands may be some of the more important factors for land cover, but ultimately, in this case, the largest potential in land use influence was the presence or absence of human footprint. The absence or presence of the refugee camp itself was a very strong control on the landslide location. And that is because a lot of the recent transient population here have deforested the slopes to provide fuel, and that has led to destabilization. And so this information was used to inform the exposure of refugees within this camp to landslides, and has subsequently been used to inform other elements of the kind of landslide assessment in this setting. So again, this is more localized work that was developed as using similar statistical approaches and Earth observation data. So to assess how well these models perform, we do want to think a lot about the different variety of methods that are used. It might be possible to train and tune your statistical model to get a perfect result, but it's important to note that that is not always going to be appropriate. High accuracy of a statistical output does not always mean a better model. And I say that because you might encounter an additional data set that you can test your model against, which then may be widely, it will show that your model is performing very poorly. And that would demonstrate that you are over-tuning your model to the input data you're using. And so the overarching point here is that to test how well a model is performing, ideally what you want is an independent data set of landslide locations. So you would take some of the landslides, if you only have access to, so for example, a one landslide inventory for your location, you would subset that, typically 70-30 is a good split, build a landslide model using 70% of the landslides, and then 30% of the landslides you would retain to assess the performance of that model. And so that's a typical way to do it, but in perfect circumstances, you have access to a secondary independent data set of landslide locations, completely generated independently from your training data to use to test the model. So in terms of quantitative assessment of performance, receiver operating characteristic curves are widely used. This differentiates, and here you can see on the x-axis the false positive rate, and on the y-axis the true positive rate. Ideally, you want a model that has low false positive rates and high true positive rates. So the closer your model is to a kind of a curve that looks like a 90-degree corner, with a corner in that sort of 0 x value and 1 y value, the better. So this model here was performing relatively well. You can see that the performance is relatively good. And to illustrate this, we can take a point, for example, at a 2%, sorry, a 0.2 false positive rate. We're capturing more than 90% of the landslides. So in essence, this is a way for us to build thresholds as well for our model that can be used quantitatively. Ultimately, you can have your level of threshold is very much dependent upon the sort of sensitivity and interest in, I guess, the accuracy, I guess your appetite for risk in some ways. If you are happy with only a very high true positive rate, you want all of your landslides to be captured, you might have to accept a higher false positive rate, and vice versa. If you really want to avoid false positives, your true positive rate might be lower. And so again, there's this trade-off between those two factors. And so defining what is an effective threshold for, let's say, a landslide hazard level might be considering the relative trade-off between the false positives and the true positives. And so again, this is a widely used method to assess the usability and quality of a landslide model. Again, want to stress that if there is a possibility of doing this with a test data set that could be independent, that is all the better. So going back to this kind of larger scale assessment of where landslides, of how landslide susceptibility models have been produced, typically these are produced at relatively moderate scale, from 10 to 1,000 kilometers squared, which is the order of like a large catchment essentially. And this image, for example, shows the size of the study area for different landslide susceptibility models. And you can see that the bulk of these, typically the distribution of these values is typically around 10 square kilometers, but can be as high as, in some cases, 10 to the 6 square kilometers. So those fewer number of studies at very large regional scale is a relevant factor, partly because we typically have to rely on inventories, and at larger scale, they may be more incomplete. And so building reliable and robust susceptibility models at those larger scales is certainly going to have to wrestle with that factor that incomplete data would be a critical element. And so one final point on this scars versus deposits discussion that we've had already, thinking about the likelihood of landslides where the scars are more likely versus where the deposits are more likely. In this case, we're comparing on the y-axis in this figure, looking at values that are higher indicate potential parameter values that are more likely to have a scar versus on lower values on the y-axis indicates locations where a landslide deposit is more likely to be found. You can see that a compound topographic index or wetness index indicates places in the landscape where lower values indicates places where the scar is more likely than the deposit, and that's, I guess, what you could imagine. And then as well, the topographic position index, which is the relative location of the landscape. These higher values indicate ridges, and that's where landslide scars are more likely to be found. And then these lower values indicating hollows in the landscape, indicating deposits. That's indicating where the deposits are more likely to be found. And so again, a lot of this seems self-explanatory. The hollows in the landscape, the concavities are certainly where we would expect to find the deposits. But the big point I want to make here is that the source areas where landslides are triggered from, that is what we must think about in terms of susceptibility. And the hazard element, thinking about where landslides are likely to impact or deposit, certainly that's more important for anyone living underneath those hill slopes and in the hazard area. Certainly must be aware of those locations and not just the source areas as well. So just an encouragement once more to think about these two kind of areas of the landscape differently, but not to sort of consider, to consider one and the other. They can't be separated necessarily in terms of the use of these studies, because we have to think about where landslides source from and where they impact. But in terms of building your models for susceptibility, it's important to stress that the triggering areas are more likely to be in these sort of landscape convexities, and more higher hill slope. So for the last part of this training, we're going to talk about dynamic hazard models. As we mentioned, the likelihood of a landslide location is we're thinking about susceptibility, but the timing of a landslide is strongly controlled by the triggering factors. So because we're thinking a lot about things that we can observe on short timelines, rainfall is a factor that is often widely observed from space, and so we can build space-based models of satellite rainfall that can be then used to assess landslide hazard. Many studies have shown that intensity and duration of rainfall are both important. The left-hand side figure here is one you maybe have seen from the first part of this training, showing on the x-axis the duration of rainfall events, and on the y-axis the intensity of rainfall events. And these points and these curves are building curves that assess the likelihood of landslides occurring at a given intensity duration threshold. And you can see again that there's a potential trade-off between longer, less intense rainfall that might trigger landslides, or shorter, more intense rainfall that might trigger landslides. And so satellite rainfall can be used to assess both of these factors. We can assess like longer-term archives of this, but any kind of dynamic model using rainfall statistics should consider this entire rainfall, the recent rainfall history, rather than just the singular value occurring at that given time. So to give an example, I could talk a little bit about the NASA's Landslide Hazard Assessment for Situational Awareness model. The version 1 of this model, or LASA, uses a simplified recent rainfall assessment to form a 7-day antecedent rainfall index. And this recognizes that for many events, the historical rainfall running up to the timing of a landslide may be up to 7 days may be relevant. In this case, the rainfall that was occurring closer to the time in question is more strongly weighted versus the rainfall from previous times. And so this was, again, a way to assess in a single value the potential intensity duration threshold. And this allowed us to build what is referred to as a binary decision tree to categorize landslide hazards. This was combined with the susceptibility model that you saw a few slides ago to build what we refer to as a nowcast system. Either you get no landslide nowcast, or moderate or high landslide nowcast based on the flow through this tree, which was, again, a simplified but effective global model that was trained with several thousands of landslides where the timing and location was known. That assessment worked very well, but understanding that there are many factors that go into landslide analysis, and that the rainfall and the susceptibility factors may not be entirely independent of one another. A follow-on version of this LASA model, Landslide Hazard Assessment for Situational Awareness, was developed. So LASA version 2 was developed as part of a project funded by NASA's Disasters Program. The static factors incorporated things like topographic variables and morphology, as well as this near real-time rainfall data and soil moisture. We'll talk a little bit about the forecast element for this in a second, as well as some of the near-surface impacts like recent seismicity. This produced using a machine learning based model to produce a dynamic assessment of landslide nowcasts and forecasts. So potential probability of rainfall triggered landslides both now and within the next several days. This was also combined with an exposure model to assess the potential impact on population, roads, and infrastructure. So here you can see the dynamic changes in the landslide nowcast. This is actually from the first version of this model, but you can see that as time goes on, particularly in the Northern Hemisphere summer that we're coming to now, you can see that there is an increase in the frequency of nowcasts, particularly in the Himalayas, but also in other parts of the world. And as you'll see as this video plays over one more time, the timing of where fatal landslides have occurred, or landslides with impacts, closely aligns with where these landslides nowcasts are observed. And so you can see again, as we get towards the Northern Hemisphere summer, there are an increase in number of fatal landslides occurring, particularly in the Himalayas, that aligns with that increase in landslide nowcasts. And this is, again, demonstrating that rainfall data from satellites can be effective at a large scale to assess the potential landslide likelihood. On a long time scale, the mean landslide probability, we've estimated this using longer term satellite data, rainfall data sets, This looks a lot like the susceptibility model, although there are somewhat slight differences. Ultimately, this is predicting the mean landslide probability for a given pixel all over the world. This is at a 1 kilometer resolution, and this incorporates data from the LASA2 model. As mentioned, this model also incorporates a forecast element, and this uses rainfall data from a number of different forecast models. This is a GEOS Here on the right-hand side is a forecast estimate for this is the islands of Vanuatu in the South Pacific. And you can see a 3-day, 2-day, 1-day, and then a nowcast estimate, i.e. like a precipitation observation estimate for landslide likelihood. And on the left-hand side of this slide, you can see landslides that were actually mapped as part of this rainfall event. So this is a very large triggering rainfall event in Vanuatu that led to a lot of landslides. Again, we were able to map those. At the bottom right here, you can see that the nowcast aligns very closely with the location of those landslides. This big red blob is basically where we see those landslides occurring. And although there wasn't a strong predictive ability for the specific event on a 3 or 2-day forecast lead time, we did see the essence of a 1-day forecast potentially flagging some of those similar kind of like locations. So again, further work is needed to build a more effective forecast model, but it's important to note that NASA scientists are developing tools to assess these systems and building together these variety of different products, both at observational data and also forecast data to assess landslide impacts. So let's use another example to assess the potential outputs from the LASA2 model, the landslide hazard assessment outputs. So here's an example from Hurricane Eta in 2020. This was a major hurricane that impacted Central America and led to a large number of landslides, particularly in some of the mountainous regions. What you can see in this larger figure here is the landslide hazard estimate for one of the specific days in this rainfall event. And you can see those large, I guess the yellow blobs are indicating where the model predicted a higher probability of landslides occurring. And when we went back and looked at the landslide mapping, we found that those were locations where, not both of those, but like one of those locations was certainly where we saw a lot of landslides. And in some of the areas where perhaps the model was still predicting a higher likelihood of landslides, there were, the model performance went pretty well here. And we'd encourage you to review the study that's in the resources here that talks about the performance of that. But again, demonstrating that the landslide hazard outputs from the model can be predictive for this kind of dynamic rainfall assessment of landslide hazard. One final note about rainfall products associated with the different landslide hazards, hazard models. Here is a slightly confusing looking figure, but I'm going to walk you through it. This is showing the potential use of different rainfall products for landslide events. So all of these kind of different categories, things, so from C15, C17, H16, et cetera, all the way to M12. Those are different landslide rainfall events. So events, there was a rainfall, a critical rainfall that led to a lot of landslides. And then the 3 types of point here are showing 3 different rainfall products, MSWEP, NASA's IMERGE product, as well as GSMAP. And the points are going from sort of the different categories from undetected to poor to fair to good. On the top side here, you can see that in many of these locations, what we're seeing basically is that satellite rainfall products in most cases detect the spatial location of landslides, but they don't always perform perfectly. Many of them only perform relatively at a fair level for some events, and some of them don't perform well at all. The general consensus amongst studies that have conducted and looked at this is that satellite rainfall products have variable skill at finding the location and timing of landslide triggering rainfall events. And there is no standout rainfall product that outperforms any of the others necessarily. And so again, combining these different data sets to make sure that there is a consistent understanding may be relevant to a longer term hazard analysis. But again, that's quite data intensive. Ultimately, it's getting the spatial correlation where the large intense rainfall that's observed, is that going to co-occur with the landslide locations? In most cases, it's done. Most of these models do pretty well, but in future, we probably want to assess why some of these locations did not perform as well, and what factors led to the rainfall being underestimated or unpredicted in certain locations that then led to landslide. So further study is needed. The last thing I want to talk about before finishing is a little bit about the runout. So as mentioned, landslides can start at the top of a hill slope and they can typically impact areas down slope. But there are many locations where intense rainfall and flooding can lead to fluidization and channelization of landslide material, and that can lead to devastating debris flows further downstream. Here's an image from Colombia, where unfortunately a very large debris flow impacted the town of Mocoa. The left-hand side figure here is like a Google Earth image of Mocoa, and you can see that the lateral spreading flow that's flagged is what we see in this photography from the aerial photography. But there's also what's referred to as channelized flow, where landslide material ended up in the river channel and flew down and flowed downstream. And that can also lead to downstream impacts as well. And so it's worth talking a bit about runouts before we close this training, because people obviously want to think a lot more about runout in the future. But understanding where runout starts and finishes is computationally very expensive, and typically requires a lot of information. One of the things you would want to think about is, for example, how fluidized that material is, like what's the total rainfall and how much does that contribute to the potential flow of this material down slope. Those kind of factors have not been effectively characterized with satellite data up to this point. In this image, we're sort of showing a predictive model estimate of where landslide runout might occur based on the volume of landslides. But again, the reason to stress that is because the volume of landslide material is also something that is strongly controlling the potential runout. And satellite observations, if you're just looking from a two-dimensional observation of a landslide, we talked about this in the first part of this training, that may not necessarily characterize the volume effectively, and you might have to use a proxy estimate or a statistical estimate of the volume of that landslide. And so again, building a volume-based estimate of runout relies upon a number of assumptions as well. And so all of these things together basically tell us that further research is certainly needed to develop more simplified generalizable models, particularly if we're thinking about satellite data. Runout typically is something that is best assessed using ground-based and localized assessment. And for community risk, certainly it's important to stress that relying upon satellite data at this stage is not necessarily productive for the assessment of where likelihood of runout risk is going to occur. And again, one of the other reasons for that is, as I mentioned before, there's this kind of channelized flow element versus the distribution or the kind of spreading of material. Those kind of elements are computationally quite complex as well. And so we really do need to think about this for future study, and I encourage anyone who's interested to talk more with us about this. But debris flow and where the debris reaches is one of the most important factors for community preparedness. And so again, solving some of these questions does matter a lot for the future of landslide science. So I have left a number of resources here, including a number of data sets that point to the NASA's disasters program and the support that they've provided for research for landslides for the last several years. Many of the studies that have been cited here are available through the NASA's landslides research website, and we can access some of that. But most of all, I want to say thank you so much for your attention and your interest in this training. It's been a deep pleasure of mine to present, and I'm looking forward to hearing more from all of you or any of you. And yeah, I'm happy to take any questions. So thank you very much, and over to you, Sean.
Thank you so much, Robert. To summarize the concepts covered in Part 3 of the webinar series, landslide susceptibility describes the areas landslides are likely to originate. Topographic factors are critical to determine landslide susceptibility. NASA DACs provide datasets such as digital elevation models, land use land cover maps, soil thickness, soil moisture, forest cover, and precipitation for modeling landslide susceptibility. Earth observation-based models typically use statistical models for generation of landslide susceptibility. Statistical models use combinations of data associated with susceptibility in combination with inventories of landslide locations. Landslide inventories are necessary to calibrate and construct susceptibility models. NASA teams have used classical statistical, machine learning, and neural network approaches to generate susceptibility models. A variety of methods are used to determine accuracy of the model. Dynamic statistical models must consider the whole context of recent rainfall history, such as intensity and duration. And NASA's Global Landslide Hazard Assessment for Situational Awareness, version 2, or LASA 2.0, maps areas of potential landslide hazard in real time. Before we move to the Q&A session, I want to remind you there will be one homework assignment accessible from the training page. Answers must be submitted by Google Form with the due date of April 1st. To receive a certificate of completion, you must attend all 3 live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after the completion of the course. Below is the contact information for Dr. Emberson, along with links to the ARSET website and social media. We will now transition to the question and answer portion of today's training. Please submit your questions and we will get to them in the order that they were received. We will post the Q&A document to the training webpage within a week of today's training. Great. And Robert, I don't know if you've been able to see, but we're getting a lot of great messages in the chat. Just but thanking you for the wonderful presentation. Is also we're getting a lot of reactions too. I see a lot of people giving the clapping reaction, so always great to see. So hopefully you're seeing that, Robert. Really great enthusiasm from the audience today. So and I want to thank everybody that's been submitting questions. We've been getting some really good ones. So I know that time is limited. So why don't we just jump right into the first one? Question number 1. In the core concept section, you noted that vegetation type and density influence landslide propensity, and that extreme wind can knock down trees and mobilize sediment. In western North Carolina, Hurricane Helene triggered slides and blew down thousands of trees, mainly at high elevations on steep slopes with shallow soils. How do you assess the risk of such factors combined, and how does this risk evolve over time from months to years?
Thank you, Sean, and thanks everyone for joining us today. I'm excited to go through some questions, and yeah, I really appreciate your interest. So to start with, I'd say that this is a really interesting and thoughtful question. Typically, we've thought about vegetation as a way that stabilizes hill slopes, but as you mentioned in North Carolina, yeah, the vegetation being blown over by intense wind did contribute to landsliding and continues to do so as slopes become destabilized. And this is something we're thinking about as a research question. NASA researchers are currently exploring how this effect persists or kind of continues using a range of data, including SAR and optical. I will add that, again, this I think is an open research question. The specific quantification of this effect remains poorly constrained, particularly at a global scale. I'd encourage you to explore some of the specific connections. I've cited a recent study conducted in Taiwan, where the impact of extreme wind is also consistently important on the overall impact on landslides. And so, yeah, there's certainly case studies exploring this, but I think a globalized general model remains does not exist yet. So this is certainly a good question and one for future research.
Okay, wonderful. Question number 2. Will high-resolution digital elevation models lead to better landslide estimates? Do we have open digital elevation model data that is finer than 30 meters?
A good question. So in general, I think you can typically say that you might be able to produce better estimates using better resolution data, but higher resolution data is not always the solution to every problem. For example, if your landslide inventory that you're using to map or to calibrate and validate the data sets, if that is mapped with an accuracy that is significantly below the level that you are using a DM, so let's say you only know the location of a landslide to within 1 kilometer, and for global modeling that would often be the case, the use of a high resolution DEM would probably be unlikely to produce and kind of accurate results, and in fact might produce like more misleading results if you're going to really high resolution. But again, if you're able to access high resolution and accurate landslide inventories, then typically finer resolution DEMs might be more appropriate and will provide you with more kind of fine detail in terms of the slope or other topographic effect. In terms of access to global, open DEM data, typically globally, the NASA data set that's available is at 30 meters. The NASA DEM data, there are other kind of commercial data, as you've noted, that may be finer resolution. In more local settings, LiDAR or other tools may have been used to develop DEMs of finer resolution, and I'm going to suggest reaching out to the Open Topography, and I provide that link in the chat eventually just to make sure that's provided. Open Topography is an excellent resource maintained by the Natural Science Foundation that provides access to DEMs around the world, free and openly.
Okay, terrific. Question number 3. How do you ensure the completeness of a landslide inventory?
This is an excellent question. And I want to really dig into this a little bit because if you think about on a long time scale, individual locations, you might think on a long time scale, any hill slope that you can consider might have a landslide. And so if you're thinking about completeness of a landslide inventory that includes all historical landslides, ultimately you're probably going to, if you want to make an absolutist perspective on this, all landslide inventories are incomplete because we haven't gone back to the dawn of time. So really, completeness is relative to the time frame over which you're looking and the area in which you're looking at. This is typically much easier to determine the completeness for specific event triggering landslide events. So one large rainstorm or one earthquake. You can look at the pre and post event imagery and including ground-based kind of validation, you would probably be able to assess the total number of landslides in a specific given area. And again, this is one of the other reasons why we are using kind of longer term analyses, including year-to-year mapping of landslides. We saw this in part 2 of the training to develop kind of multi-temporal landslide inventories to assess the change year-to-year. That, again, would help us build a more complete inventory for each given year. And ultimately, this is useful because then we can, any susceptibility or hazard model that we output is a function of the time frame over which we've mapped those landslides that are used as input. So again, we would probably say that or a susceptibility model is a susceptibility for landslides likely to occur in the next X number of years that will be relative to this. So again, this is something that's considered that's very much on the availability of data or the availability of information for your specific area. So the value, the quantification of this will vary, but just want to make sure that you think about the kind of the specific framing of completeness, what you mean by completeness. And one final thought here is that, again, cloud-free imagery often is the most critical factor to determine completeness when mapping from satellite data for specific events. And so that's just one other note, and we can make sure we get cloud-free imagery.
Okay, wonderful. Thank you, Robert. Question number 4. Can landslide susceptibility for an area be significantly affected by forest loss due to wildfires? Do you have any examples where this was observed?
So really, yeah, this is a really important question and one we have not talked a lot about in this specific training. And I think that this is certainly ample opportunity to kind of lay some seeds for maybe future exploration of this. Yes, in short, forest loss due to wildfires is a significant control on potential for landslides in a given area. And it's not just the loss of trees, it's also the way in which intense heat from wildfires and ash can significantly change the overall the surface hydrology of a specific area. In many cases, very shortly after a fire, the porosity of the surface decreases, which means that the overland flow can increase from water, which increases the propensity for debris flows. So this is a known effect, and the United States Geological Survey maintains a very detailed set of analyses of post-fire areas in the US and the potential for landslides and debris flows to occur in those settings. I've added the link here. So lots of examples in the United States and internationally too. I know that there are several examples in the literature in Australia, as well as in Africa. So again, there's plenty of cases where this matters a lot. The specific role of, let's say, forest loss versus change in surface hydrology has been tested, but I think in general we don't have a globalized model of like how those factors kind of contribute over time. So something to consider for future research, and developing a global post-fire landslide susceptibility analysis is something we're also looking at NASA as well.
Okay, terrific. Question number 5. How can risk models be accessed and tested in a specific area of interest?
So we, as the NASA's Landslide team, the disasters program, don't maintain specific risk models for any given area. What we do is to typically develop methodologies to provide generalized approaches to look at this in your own area, and reproducing those methodologies is something that we would happily talk to you more about if you reach out directly to us. I think the best advice I can give is to explore the available literature and the open source sort of research, as well as specific locations, as well as reach out to us more generally to sort of determine if there are overlaps with areas we're already aware of. So yeah, I think talking in general terms, we don't have that data set, we have that data set to hand, but we have to talk more about like how we can help develop those approaches. So.
Okay, terrific. Question number 6. Have any of these analyses been checked with ground truth data, or have they only been developed with satellite images?
Yes. So for many of our local scale, for the majority of the local scale work that we've conducted, we do use ground-based validation. And so the work that's been mentioned in parts 1 and over the several parts of this training, and particularly in Rio de Janeiro and Bangladesh, ground-based assessment of landslides was used to validate and calibrate the susceptibility and hazard models. More generally, globally, we obviously use a range of different data sets as input to the global susceptibility analyses, including the Global Landslide Catalog, the GLC. It's important to note that that catalog specifically consists of observations from ground-based assessment, typically either from national inventories, media reports, or from other sources that may be kind of, again, collected from ground-based rather than specifically satellite-based inventories. So we consider that we have a kind of sort of semi-ground truth data set is used to calibrate. And again, we then use additional sources of information where possible to validate that as well. So satellite imagery forms a part of the way we develop susceptibility analyses, but typically is certainly not the only part. And for local assessment, we certainly use ground-based data as well. So.
Okay, wonderful. Question number 7. Is the LASA model open source? Is it possible to train the LASA model on a country-specific or area-specific data set?
Yes, so I'd love to be able to point this out. So the model is open source. We have both the research papers developed to the research paper published discussing LASA are all openly available through the NASA Landslides research team website. And I'll post the link in the chat as well. The code specifically is available through our GitHub. This is for both version 1 and version 2 of LASA. So implementing a version of that should be feasible in anyone's systems. In addition, the code is all maintained through open source systems, so Python-based. So again, it should be replicable on any source tool system. You also asked about how to train LASA on country-specific or area-specific data. This is something that has been done. So as I mentioned in the first part of this training, Rio de Janeiro, the city of Rio de Janeiro implements a specific version of LASA. They have a bunch of different inputs and outputs that are kind of controlled by their parameterization and their inputs. And yes, they certainly are training it on that. So it has been demonstrated. I think the general answer here, though, is please reach out to us to discuss how that would work. It's important to note that the quality and detail and depth of a landslide inventory is often the most important factor that helps determine how we can develop something for country-specific or area-specific LASA, and more generally, the availability of other data sets that would include rainfall data or kind of other local. So there's a lot of inputs that would go into a LASA model, and just because you have your own country-specific landslide inventory does not necessarily mean that it's going to completely translate. So again, this will all depend on what you have available, and so we encourage you to reach out to us directly to kind of talk more about how we can help support that that further development. So thank you.
Great, and it seems like there's a lot of interest in the LASA model. Question number 8, in the LASA 2 model update, why has snowmass been excluded?
Yeah, so I think we took the perspective that the most important thing to calibrate and validate the dynamic landslides assessment is the timing of landslides as well as the location of landslides. And obviously we need a certain quantity of information to validate effectively. We determined that there was not sufficient information regarding timing of landslides and location of landslides in areas where snowmass was contributing, particularly considering that the snowmass changes dynamically as well. And so that element was, I think, a strong control on how we wanted to kind of explore that factor. And so again, for those settings across a variety of settings is certainly necessary. And we typically would not be able to, even if it was 100 landslides in a small area, I think that would still be insufficient considering we need a larger range of landscapes to validate on as well. So it's certainly a data question at this point, and I think whilst that is of interest in the future, at this stage we're not exploring that. The other thing I suppose that's worth pointing out is that the iMerge data that is used as part of the rainfall to sort of understand how rainfall triggers landslides within the LASA model, that data is there is a latitude limit to how far north and how far south that information is collected. And whilst that is not a strong control on the southern hemisphere landslide model. In the northern hemisphere, it does exclude some larger parts of northern Russia and kind of east and northern Europe, as well as parts of Canada. And so there's kind of very kind of like higher latitude areas where snow mass may be significant. It's just not covered by the IMOJ data. And so again, we don't have a lot of strong information regarding the sort of rainfall element to kind of use in those locations as well. So it's a kind of data volume and both in terms of the landslides as also the rainfall element. So.
Great. And I saw a thumbs up from Sonia, so it might have been Sonia's question that was asked. Question number 9, is it possible to predict the intensity of a landslide? If yes, how?
Ooh, that's the $1 million question in some ways. So I think I am not aware of any global models that have been developed that can predict the sort of, I guess the big question here is the intensity of a landslide, thinking about the volume of material that's mobilized. And at a global scale, I'm not aware of any model that predicts the kind of specific volume coming from a landslide. And ultimately, that's partly because larger scale models are statistical in nature, and so they would ultimately predict the kind of likelihood of a landslide across a larger landscape. The size of a given landslide is going to depend a lot on the very specific factors for that individual hill slope. And I know no one who is prepared to build a model that is predictive of individual hill slopes at large scale. And that is a reflection. We just simply do not have the accuracy of that information to. Now, locally, I suspect different stories may be relevant, and this is where I think I would encourage you to review some of the literature, whereby for individual areas where there is a known risk of landslides for highly susceptible hill slopes, it might be possible to assess, for example, the location of given fault plains or other sort of weaknesses within the rock mass that might develop potential for a large kind of specifics of that area and the kind of likelihood of a fault plane, of a failure plane occurring at a given depth. The other thing to point out is that just because a landslide is small does not mean it is not devastating. And there are some really significant examples where we can see individual boulders that have rolled down hill slopes and then rolled through a town, or even sort of examples where cars have been caught by sort of small landslides occurring on road segments. I think we tend to think about landslides as a devastating event, large or small. And again, certainly larger landslides can cause more impact, particularly as debris flows. But we tend to take the perspective that predicting whether things are going to be large or small does not give us false sense. It could give a false sense of security that a large landslide or a small landslide, a smaller landslide may be less dangerous. And I think that's something we want to avoid, making that assertion. So yeah, it's a really good question. And again, I think a really important research question. But from a hazards and risk perspective, it's certainly, again, important to note that size and impact are certainly not necessarily correlated.
Okay, question number 10. Which is recommended for better landslide susceptibility assessments? Considering all available, including historical landslide inventories, or considering more recent landslides for, say, the last 5 to 10 years?
So, yeah, I think, again, this is going to come down to what the definition you're using here for what the word better is. And that sounds like a kind of a hedged answer. And in some ways that is because it is. It will very much depend, again, on what your use case is. So longer-lived, longer-term historical landslide inventories, such as those that are maintained by state geological surveys in the United States, as well as in some of the international locations, may help constrain the likelihood of larger, deeper-seated landslides that may occur at kind of larger scale. Those kind of longer-term risk assessments of potentially slow-moving landslides as well may be really relevant to structural engineering assessments of like local setting of cities and so on. The way that we've approached landslide mapping from satellite scale, but particularly at the NASA team at Goddard Space Flight Center, is to look at these shallow, fast-moving landslides that can be typically very easily observed using rainfall, predicted using rainfall data, as well as estimated and mapped using observational optical data. Those landslides typically occur on short time zones, triggered by rainfall, and the recurrence interval for those can be relatively short. So on the order of the last 5 to 10 years, you might see a landslide occur, revegetation of that scar will then occur, and you will no longer see it in the landscape, and then potential for it to reoccur on that 5 to 10 year timeline might be important. So typically, I think if you're thinking about shallow, fast-moving, catastrophic failures like that, maybe your shorter-term landslide inventory may be more relevant. But like longer-term historical landslide inventories again, this is a guideline, not a fast and hard and fast rule, but maybe more important for assessing the kind of larger scale potential for slow moving and like larger landslide impacts. So again, this is something to discuss. If you're really interested in learning more about this, I'm happy to kind of reach out. And I think this is certainly a topic that we could explore in more detail. So thank you for the question.
Okay, terrific. Thank you, Robert. Question number 11. How does soil moisture influence the occurrence of shallow landslides at a local scale? How can INSAR technology revolutionize the integration of soil moisture data and landslide monitoring to develop a more effective hazard prediction model?
Very thoughtful question. So you're absolutely correct that soil moisture has a strong role in influencing the potential for landslides to occur. You can imagine that increasing moisture in the soils, increasing the saturation state of the subsurface, has a strong control on the potential for landslides, particularly when you add to that a sort of like either seismic shaking or a triggering rainfall event. And so increased soil saturation may have a strong role in, again, increasing susceptibility. So we certainly know that the soil moisture tends to be a correlating factor. And in fact, in the last two models, soil moisture is included as a factor that is helped to predict the likelihood of landslides in given locations. We, in this case, used the global SMAP dataset, so soil moisture active passive. That's a microwave-based dataset. And again, that's partly because it's a globally available near real-time dataset that we can use to characterize the soil moisture dynamically. INSAR data and SAR in general can be used to characterize surface and near surface soil moisture, but the swath of those values is typically smaller, and the return period of that data is typically slower than the microwave data sets that are available. So I think for a given location, you are likely to only get a return period for a SAR satellite or INSAR data on the order of 7 days right now at best. I think that may improve when NISAR is launched, but in general we may be unable to characterize the soil moisture on a time frame that is necessarily what we need to characterize the kind of the dynamic changes. But again, if you have access to like more low latency and higher frequency data, that may certainly be a control. So again, an interesting research question. As mentioned, we still typically use microwave-based data, and INSAR has not been employed in that case for us yet. But again, happy to explore that more with if you have thoughts and questions, please reach out.
Okay, thank you, Robert. Question 12. Can HAPS, or high altitude pseudosatellites, provide real-time data of runout zones when a disaster is happening, like Valencia Dana floods?
So really interesting question, particularly because I have never come across the term HAPS or high altitude pseudo satellites before, and I'm going to have to go and research that, and I'll provide a more detailed answer to this in the final version of this. But just while I'm talking about it, I will note that flash floods and runout from kind of debris and so on is one of the most challenging elements from satellites more generally, I think, and you will clearly, I think most people understand that satellite return period is every day at best, or every 7 days in some cases. The ability to map the time, these very short-term, the ability to capture these very short-term flood bursts is very difficult, and it's something we have challenged with a lot in the disaster space at NASA as well. So I'm going to explore more about this, and I think this is a really interesting potential answer. But I don't want to kind of pose a guess, so I'll give a full answer later on.
Okay, question 13. Can geological factors such as the contact between two lava flows, example given weathered basalt and compact basalt, contribute to landslide occurrence? Additionally, can geospatial techniques help in identifying and mapping these lava flow boundaries for landslide susceptibility assessment?
Interesting. So I suspect you have a very specific case study in mind, which sounds like a really interesting one in general. You're absolutely right that the potential changes in the sort of either the mineralogy or the fracture density or various kind of geomorphological factors may strongly influence the potential for landslides. And certainly structural contacts are often a location where failure plains can occur. I think volcanic terrain has its own specific set of challenges when it comes to landslides because we know that there are other factors at play, including, particularly if there's active volcanism going on. But I think, yes, in general, geological factors can certainly influence the landslide occurrence. In terms of geospatial techniques that can help in identifying these lava flow boundaries, that's something that I think would depend a little bit on, let's put it this way, the spectral characteristics of the landslides are what we would use to have to distinguish between those elements. And that would, for example, be whether they look, optically different, if they have different spectral frequencies, spectral intensity in different wave bands. Hyperspectral data has often been used to explore differences in surface mineralogy. And so if there is a clear differentiation between those lava flows that you're interested in, hyperspectral may be a way to explore those differences. There are a number of RSET trainings on hyperspectral data sets, and I think there's a link in the resources section. Optical data can be used. I know that I've done field work in settings where optical data can be used to delineate between lava flow boundaries, but that's not a general rule, and it would depend on the specific locations. I think it's generally going to depend on the spectral characteristics of the two lava flows that you're interested in, but in theory, possibly. So, yeah.
Okay, terrific. And last question, number 14. Which NASA Earth system datasets or remote sensing techniques are most effective in detecting lithological discontinuities, such as lava flow boundaries, that may influence landslide susceptibility?
So I suspect this is the same person asking this question as to the previous one, and I'm excited to see their interest in this specific element. So again, I would say, again, it's going to very much depend on the spectral characteristics of the landslide of the lava flows in question. Again, as I mentioned before, hyperspectral data has been used in the past to distinguish between surface mineralogy, and so it might be a tool that could be used in the setting. But there are likely to be other resources that I don't have at the top of my head right now that I will dig into and make sure that there is a more detailed answer. I know that, for example, the USGS volcanic program and NASA scientists working on volcanoes as well have looked at these kind of elements, and I'll make sure I have a more detailed answer in the final version of this. So thank you.
Wonderful. And thank you to everybody that asked questions today. We got some really great ones. Dr. Emerson, as we wrap up this final part of the webinar series, I just wanted to ask if you had any thoughts or comments to the participants that were joining today.
Well, above all, I want to say thank you so much for all of your time and interest in this topic. Have been really excited and interested to present to you all. I think this is a really interesting topic, and just from my own personal perspective, but I'm glad to see that a lot of other people have been keen to be involved. And again, if you have further questions, please do reach out. We're always happy to hear from interested researchers and scientists and members of the public. And I encourage you to check out the resources and include our citizen science landside mapping tools as well. So if you're interested in following up on that. But above all, I want to say thank you to the RSET team. Thank you to Sean. Thank you to all the support staff who've been tremendously helpful in putting this together. This has been a team effort, and I'm really glad to have been part of it. So thank you.
And Robert, thank you so much. Hopefully you're seeing some of the reactions coming in from participants today. A lot of great, also in the comment, a lot of great conversation in the chat for thanking you for such a wonderful job that you've done for all three parts. To Dr. Emerson, thank you so much. And as you just alluded to, I want to thank the RSET team, Natasha Johnson-Griffin, Brock Blevins, Selwyn Hudson-Odoi, and Sarah Cutshall. Thank you all for supporting this training and making it a success. And finally, I want to thank all of you joining today. We hope that you got a lot out of this training, this three-part training, and we hope that you'll join us soon on an upcoming RSET training. So thank you all, and be safe.